All right, welcome back to another example video. This is a companion video to lecture 6, and we're going to talk about reducing computational models to each other. So what that means is that we're going to take some model of computation, like an automaton that can accept or reject strings or do other things, and show that some other model can do precisely what it can do, vice versa. So the relevant pages in CIPSR are pages 177 to 179, if you'd like to check some of this out in the textbook. So I want to start today with the Church-Turing thesis, which is an informal thesis that tells us our intuitive notion of algorithm is more or less exactly what a Turing machine can do. This is a hypothesis, it's not a theorem, but we see over and over as we define new models of computation, they seem to be either equal to Turing machines in power or less powerful, like our previous automata. So we should expect that when we give a Turing machine a superpower, either it's a reasonable superpower that meets our intuitive notion of a well-specified process, in which case a Turing machine can probably emulate that superpower, or it's a truly magical superpower, which we shouldn't expect to implement in the real world. So to show that a Turing machine is equivalent to another model, we need to reduce from the Turing machine to the other model, that is, show any TM can be simulated, or equivalently, any computation performed by a Turing machine can be done by the other model, and vice versa. We've seen this already in the textbook for multi-tape TMs, which you can look at that on CIPSR page 177, and for non-deterministic TMs, which you can see on CIPSR page 178 to 179. I'm going to do a couple of other ones today, but just like multi-tape and non-deterministic Turing machines, we're going to find out that if we give a Turing machine an additional power, it turns out to be equally powerful. So our first example is a Turing machine with a stay put operation. So normally our Turing machine's transition function says, hey, give me a state and give me some symbol that I'm looking at on the tape, and I'll tell you where to go, a new internal state, what to write on the tape, so a new tape symbol, and whether to go left or right. So this new stay Turing machine can do all of those things and has one additional power. It can stay put. So we want to show that these two things are equivalent. So first, we want to show that anything a Turing machine can do, the stay put TM can do. And I claim this is trivial. Why is that true? Well, if you have some Turing machine operates in a certain way, you can emulate it with a stay Turing machine by just copying the Turing machine over and not using the stay put operation. The stay Turing machine is strictly more powerful. However, if we want to show that our Turing machines can do anything the stay put Turing machine can do, we're going to have to do a little bit more work. So strategy 1 for reducing a stay TM to a TM is, given a stay TM, replace transitions that use the stay put operation with pairs of transitions that do the same thing, move left, and then move right. So this is one natural way to do this. If I'm looking through the description of a stay TM, I can just pick out every time I see switch this symbol to this symbol, move states, and stay put. And I can replace it with two transitions that'll transition between the same two states, write the same thing on the tape, but that action will be split up into a left move and a right move. Strategy 2, even simpler, is going to be simulate a given stay TM with a regular TM. So we can cash that out in terms of, if you give me a stay TM, I can build a TM that will write its state diagram down on the tape for starters, and use that state diagram to compute every move and manipulate the input. That's one way I could simulate it. I could also copy the instructions. But sometimes the easiest way for me to think about it is just imagining my Turing machine as having my stay TM's description on the tape. It'll write that down. It'll move the input over, and then it'll use the stay TM's transition function to manipulate the input. So whatever input it has at the end, we'll consider that the output of the simulated stay TM. A slightly harder example, potentially, is the Turing machine with doubly infinite tape. So this goes a little bit beyond the stay TM, because it doesn't just have a new operation, it's actually got a different memory structure. So our normal TM on the left can move left and right, can read from the tape and write, but whenever we hit the left side of the tape, we'll just stay put by definition. And this new kind of TM, I'll call it a TM sub 2 for doubly infinite tape. It's allowed, after it reads in the input, it can move left, it can move right, it can move way over here and write things on infinite tape squares stretching out to the left as well as the right. So reduce Turing machine to a Turing machine with a doubly infinite tape. I claim this is pretty much trivial. So a Turing machine with a doubly infinite tape is almost strictly more powerful than a regular Turing machine. The only thing we've got to do is add a rule to bounce back if we move L from state 0. In other words, we can simulate any regular Turing machine with a Turing machine with a doubly infinite tape. We just have to make sure, I shouldn't say state 0, I should say tape square 0. If we're in this tape square 0, our simulating doubly infinite tape machine will just have to ignore L's and, in fact, stay put, which it can do by simulating our stay put machine. Now, suppose we want to reduce a Turing machine with doubly infinite tape to a regular Turing machine. In this case, we can simulate a Turing machine with doubly infinite tape, but what are we going to do when we move off the left end? When we start reading and writing on these squares that don't exist in our simulating machine? Well, we can do the following. So we'll start, we'll say, given a TM2, which I'll call M, we can simulate it with a TM M prime by first following, I'll say emulating the execution until we move left from state 0. In other words, we're just going to simulate our TM2 and we can simulate it as normal until we move left from state 0, at which point our TM2 has moved on to a square, which our TM does not have on its tape. We can't follow. At this point, pause our simulation and run a subroutine that shifts the tape contents right 1 square. So as a picture, suppose this is our simulating Turing machine, and we have reached the point where we're at the left side of the tape, and the machine we're simulating wants to move left. Say our tape contains A, B, C, D, dot, dot, dot. What we'll do is we'll pause the simulation, and we will run a subroutine that moves the whole tape contents over 1 square to the right and fills the new square with a blank. And then we'll resume where we left off. We can now move left onto this new square with a blank. Then we will resume from step 1. So in other words, whenever we need to use this extra space off to the left, we'll move our tape over to the right and give ourselves some more extra space. And in that way, we can use our singly infinite tape to simulate a doubly infinite tape. So in conclusion, to keep your eye on the ball, what are we doing here? Well, we've defined other automata, things that seem slightly different from Turing machines. This is always okay. We can build any automata we want as long as they're well defined. We want to show that these two things are equivalent in power. Our new automata and our Turing machines can do exactly the same things. So what are our 2 steps? We've got to show first that anything our old Turing machines can do, the new ones can do also. We've got to switch it around, vice versa. Anything the new Turing machines can do, the old ones can do. So that's what an equivalence reduction will look like. Thanks for watching, and I'll see you in class.